Good evening students. So now let us start with the next topic, that is the frequency shift keying. So what is the frequency shift keying? As we discussed in ASK, like there is a analog carrier wave at the input and there is a digital or the binary modulating signal or the information signal. These are the two inputs. One is the analog carrier, another one is the digital modulating signal. So now in this case, the digital modulating signal is going to modulate or modify or shift the analog carrier by changing its frequency, right? So that is why it is the frequency shift keying. So in this case, the frequency of the analog carrier is going to be shifted by the binary or the digital modulating signal or the information signal. So this is the frequency shift keying. So let's see from, let's refer our notes together. Either if this screen or this background of the video is not clear to you, then you can open your notes separately. It is the same material that I have already uploaded for the FSK and PSK, and I hope that you have completed these notes in your registers as well. So it's better that if you open your registers along with this video, or if it is clear, then obviously you can see the background of the video, which is the same material. So let's start. It is a form of constant amplitude angle modulation similar to frequency modulation. Yes, it is similar to frequency modulation, because in this case again we are going to shift or change or modulate the frequency of our analog carrier using the modulating wave, except the modulating signal is a binary signal that varies between two discrete voltage levels. So yes, it is a form of the constant amplitude angle modulation similar to frequency modulation, except the modulating signal is a binary signal which varies between two discrete voltage levels. FSK is also called as binary FSK, Bpsk. So as we have discussed earlier, every modulation has its characteristic equation. So the equation of the FSK wave, that is a frequency shifted wave, frequency shift keying, that is the digital version, wave will be as given in the equation 2, that is Vfsk is equals to Vc cos 2 pi Fc plus Vmt delta f into t. Obviously Vfsk represents the binary FSK waveform, Vc is the peak analog carrier amplitude, Fc is the analog carrier frequency. Now note that here delta f is the peak change or shift in the analog carrier frequency. Vmt is the binary input modulating signal. So here in this expression, delta f represents the amount of frequency shift that is going to occur in the analog carrier frequency. Fine, is that clear? So there are two frequencies here, in fact three. First is the carrier frequency Fc, which is the frequency of the analog carrier wave. Another one is the FSK, which is the frequency of the frequency shift keying wave, and there is delta f, which is the peak change or the shift in the analog carrier frequency. Now again we will take the two cases. First case is the logic 1, that is in which we take the high of our binary input information signal, that is the input signal that is in the digital form, the information signal is in the digital form. So we take the two cases, one is the logic 1, that is when it is high, and other case is the logic 0 when the wave is at low. So first case is logic 1, so Vmt will be plus 1. Now put this Vmt plus 1 into the equation number 2. So after putting Vm as 1, we get this equation. Just see in the notes that Vfsk is equals to Vt cos 2 pi Fc plus delta Ft. So from this equation we can infer that frequency increases for binary input equals to 1. Obviously, because now the expression for the logic 1 case is showing that Vc cos 2 pi Fc plus delta f. So now we are adding some frequency to the carrier frequency. So in this output wave, there is a shift in the frequency towards the positive side. That means the frequency of the modulated wave is increasing. So frequency increases for the binary input 1. Now let us take the another case, that is which is the case to logic 0. In this case, let us put the VMT as -1. So now put the VMT -1 into the equation number 2. What you will get? We will get VFSK is equals to VC cos 2 pi Fc minus delta Ft. So in this case, frequency decreases for the binary input 0. Now if you draw the frequency characteristics centered at carrier frequency, as you can see that at the middle there is Fc, which is the carrier frequency, around which we will get our output frequencies. So one is Fm. What is the Fm? That is the mark frequency, which is Fc plus delta F, or you can say the upper limit of the frequency. There is, to the left of the Fc, there is Fs, which is the space frequency, which is Fc minus delta F. So if you see the band for the logic 1, there will be Fc plus Fm, right, that is towards the Fm towards the right hand side, and for the logic 0 you will get the Fc minus delta F, that is the Fs, that is the space frequency. Now difference between Fs and Fm is equals to 2 delta F, as you can see, right, delta F minus of delta F will give you twice of delta F, that is the difference between Fs and Fm. So frequency deviation is referred as the difference between either the mark or space frequency and center frequency, or it is the difference between the mark and space frequencies divided by 2, because the difference between the mark and space frequencies is twice of delta F and then twice of delta F, and then we have to divide it by 2 to get the difference between the center frequency and on the either side band. So delta F is equals to mod of Fc minus Fs, or equals to Fc minus Fm, or equals to Fm minus Fs divided by 2. This gives you your equation number 3. Now just observe the image, that is the graph given in your material. For the binary input 1, you can see the frequency is increasing. Just see the figure given in your material. So this is the Fm part, where when the frequency is more, that is under the logic 1, it is Fm. Whenever there is a logic 0, the frequency decreases and it is space frequency Fs. So I think now you can understand the graph very easily. The graph is showing one of the binary input, that is our information signal or the modulating signal, and below that you can see the Fsk output, and our Fsk output is the analog output. So according to the binary input, you can see our analog output is changing. Whenever the binary input is 0, our frequency is decreasing, that is the space frequency, you can see Fs written over there. Whenever the binary input is 1, the frequency is increasing and it is Fm, and so on, alternating for logic 1 and 0, we are getting Fs and Fm. So you can, it is well explained in the table as well, the same thing in the diagram. Now let us come to the baud for the Fsk. So baud in this case obviously is Fb, frequency per 1 bit transmission, that is your baud. So maximum bandwidth in this case will be Fs minus Fb minus of Fm minus Fb. So Fs minus Fm, the minimum bandwidth will be the difference between the space frequency and the maximum frequency or the mark frequency, that is equals to 2 Fb, right. Now Fs minus Fm is minimum bandwidth will be equals, I think you are able to see in the notes clearly. So after that Fs minus Fm mod is twice of delta F, so minimum bandwidth will become twice of delta F plus Fb. This gives the equation number 4, or this is also the minimum Nyquist bandwidth, where delta F is your frequency deviation and Fb is the input bit rate. So this ends with our frequency modulation. For every part for every this ASK or whether it is FSK or whether it is PSK, you should remember three things. First is the definition, that is what is happening, like what is the input, and the input is changing which parameter of your another input wave and what you are getting as an output. The answer to that is there are two inputs. Remember, one of the input is the analog form, that is the carrier is in the analog form. Another input is in the digital form or the binary form, that is our modulating signal or the information signal. And what we are getting? We are getting output again in the analog form, that is either ASK or FSK or PSK, right? Now, according to our logic 0, then the second thing that you should remember in all the three cases is that according to the logic change in the input, that is in the modulating signal, whenever there is a binary low or the binary 1, our carrier is going to change and the output is going to change accordingly. So, in the ASK form, in the ASK case, the amplitude of the carrier is changing, and you can see at the output that ASK amplitude is changing according to the your modulating signal logic 0 or 1. In the FSK, frequency of the FSK output wave is changing according to the 0 and 1 logic. And in the third case that we are going to next discuss is the PSK, in which the phase is going to vary, fine. Then the third thing that you should remember is the characteristic equation or the equation that governs the output wave. And then along with the equation you should know that how the logic 0 or logic 1 will result the or will change your equation of the respective modulated waves. So, three things that you should and the fourth thing is your bandwidth. So, there are four parts of every modulation in this. First is the definition, second is the characteristic equation, third is the cases according to which you are going to derive that what is going to change in the output, and number 4 is your bandwidth or the baud and the relation that what is the minimum bandwidth, maximum bandwidth or the deviation, right. So, now let us start with the last part of this digital modulation, that is the phase shift keying. Now, this phase shift keying is similar to conventional phase modulation, right. It is as the FSK was similar to FM. So, in this case PSK is similar to the PM, that is a phase modulation, except with PSK the input is a binary digital signal and there are a limited number of possible output phases. Okay. So, it is quite similar to your phase modulation, but in this case the first difference is that your input wave or the information signal is in the digital form or the binary form, and there are limited number of possible output phases, right. So, let us read further. Input binary information is encoded into group of bits before modulating the carrier. Number of bits in group ranges from 1 to 12 or more. So, let us consider an example. Consider the number of bits given by capital N, and the number of output phases is defined by m is equals to 2 to the power n. So, if let us say we are considering n bits, then the total output phases will be 2 to the power n. So, let us say we take the 1 bit, so the output phases will be 2 to the power 1 is equals to 2, and for n is equals to 2 the output will be 4 and so on. So, for binary phase shift keying, that is for the Bpsk, n is equals to 1 and m is equals to 2, that is there are two phases are possible for the carrier. One phase represents logic 1 and the other phase represents logic 0. When the input digital changes state from 1 to 0 or 0 to 1, output carrier shifts between two angles separated by 180 degree. Hence, it is called as phase reversal keying and biphase modulation. Now, just concentrate on this diagram or the graph. We can see there is a binary input, right. So, first of all, before modulating the carrier, our binary input is taken into the as written before, just read that line. Input binary information is encoded into groups of bits before modulating the carrier. So the number of bits in the group ranges from 1 to 12 or more. So you can see in the diagram, first of all, this binary input is encoded into the number of bits, right, and corresponding to the number of bits there are output phases, right. So just see, whenever, so this is a binary input where you can see 1 0 1 0 1 0 alternate. So it is a simple binary wave, and you can say TB is the time for each bit, right. TB, as in the ASK we saw that there were TB and TS, here also this TB represents the time period of one bit. Now just see the Bpsk output. What is happening when input digital signal changes from 1 to 0 or 0 to 1, the output carrier shifts between the two angles separated by 180 degree. So whenever there is a change in the input digital signal, either from 1 to 0 or 0 to 1, there is a shift in the phase of the carrier. So just see the diagram carefully, you will be able to see the shift in the phase of the output according to the change in the change in the digital signal, either from 1 to 0 or 0 to 1, and that is how you are getting the phase reversal keying or the biphase modulation. So you can see for the first case you are getting the 0 degree phase reversal, and then from the next, in the next part you can see pi, that is the 180 degree phase, then again 0, then pi, then again 0, then pi, and so on. Pi and 0 is written in radians, that is the phase shift in radians, and 0 and 180 is written in the phase shift in degrees. So in one case, now if you compare this with your equation, in the equation it must be happening that one is the sin omega ct and other is a minus sin omega ct. It is just showing the phase shift by 180 degrees, the negative sign. So that is how it is done. So I think we are done with this pulse coded modulation types, that is the ASK, FSK, PSK. So you just remember the you should be able to, after going through these two lectures, you should be able to compare the three modulation forms, that is the amplitude shift keying, phase shift keying, and the frequency shift keying. And after covering this up, I guess you will be able to solve the next two questions. I think 3 more questions are there in the assignment over frequency shift keying. So now you all set to go and solve the assignment, and we will discuss that assignment in our next video lecture. All the best.